Okay. Yeah, all right. So this is indeed very related work to what we have just heard, and I'm very grateful to the organizers for the nice combination of these talks. So in this talk, I'm going to speak about how you marry three different interesting features of HRL into one box. Interpretability on one hand, and support for subgoal discovery on the other hand. And the feature of reward freeness. So this is a model which can live with a reward or without it. It doesn't actually make any difference. So this is my colleague Alexander is here, so he will be answering question as well if you have one. If you have some questions, but please be free to interrupt me anytime. So would be pleased to answer your questions anytime during the talk. So I think I will switch my camera off for the sake of the bandwidth. Just a second. Okay. So first of all, I'd like to spend some time for some kind of introduction of the context in which we are working in the region of our work. Actually, many of you might know the common idea that you have, if you have some classifier which tells you the connection between the combination of features of one to fk to some other feature and tells you the probability of this relationship, then you can build some RL model on top of this classifier. Well, in particular, here, if you have a state classifier which takes a state description in terms of features and tells you how good this state is for you with some probability, then actually you can use this information for building an RL model. And this idea has been used, for example, in the option chaining architecture, where you have a goal and you discover some important intermediate states being classified as good ones. And then you go to these states and ask how you reach them consecutively. So you have a primary goal G, and you have identified some good state G2, and then you ask how you can reach G2 from another states, and you classify some another G1 as good state for reaching G2, and so on. You build a chain of options which leads you to the primary goal G. But if you look at this classification test, then actually these relationships are, well, they can be seen as logic rules, like implications between state description and the feature. Well, when we were students, we got interested in logic-based ML in the broad sense, and we were connected to the Siberian School of Artificial Intelligence, represented by Denis in particular, who was developing an approach to logic-based ML. And the basis of this approach was that you learn some rules. For instance, the rules of this form, where you have, well, we use these rules, for example, for solving robot locomotion tasks, the videos you see in the slide. For instance, we use the rules of this form, which describe sensor indications of robot models and actions, and reward which is going to be obtained after performing this particular sequence of actions while having this particular sensor indication. So these kind of rules we use for solving robot locomotion tests, and this was quite successful. We made some experiments, and this could be actually a topic of another talk today. But this particular talk is devoted to another problem, which is related to long-term credit assignment. So in the first step, we were using this rules-based approach for solving exponential explosions of action combinations. So if you have a robot, you can have some combination of models, which gives you a very big, very large action combination space. And learning this space is actually very difficult. And it has turned out that rules can be used for solving this task of exponential explosion, this problem. by employing some functional symmetries which can be encoded in rules and well, motivated by the structure of the robot. So actually the explicit form of the rules can encode some structure of the robot, and this structure, this symmetry can be used in order to improve the efficiency of learning, even if you have lots of actions, lots of possible actions. So after this test, we moved, as I said, to the long-term credit assignment test, which was the question for us whether we can use a similar approach, rule-based approach, to identifying subgoals in environments which help you in well, reaching long-term goals or obtaining long-term credits. So this is the talk. This is the topic of today's talk. When we looked at papers describing HRL, hierarchical reinforcement learning approaches, we saw that, okay, so most of the approaches are continuous, so they deal with continuous differentiable models, they can deal with continuous environments, and yeah, surely it's the progress well made in the last years, which allows for dealing with continuous inputs, like images, videos, and etc. Discrete models are like rare animal nowadays. However, on the other hand, if we look at about this, we think that lots of business tasks are actually discrete tasks. Lots of data the business has is actually discrete data. I will talk about it a bit later. So it's a question for us whether we throw out discrete worlds and discrete models as a separate animal at all. From the other hand, if we look at explainability of HRL models, we see that, yes, many of them are black box. Some of them are augmented with some tools of explanations, which are built on top of RL models as a separate add-ons. And only a few of them are infinitely explainable or interpretable when read broadly. I mean, only a few of them allow for learning explicit algorithms, which you can read off as a human, you can understand and interpret in your mind, understand what's going on, and maybe debug or apply in different situation or verify, etc. In this sense, this is exactly what the previous talk was about. And finally, when we look at another dimension of HRL, namely how deep subgoal hierarchies are supported by today's models, we see that most of models actually support only fixed hierarchies of subgoals. So, for example, up to n subgoals, where n must be specified as a parameter of the model. And only a few of them do not have this limitation. And actually, these blue ones, are actually the black box models, and these are exactly the continuous models which we observe in today's approaches, in today's papers. When we look at environments which could be helpful in evaluating different HRL models, in evaluating the performance of subgoal discovery, we see some, well, old environments like taxi tasks, where we have only a fixed set of subgoals, like here in taxi tasks, we have only a single subgoal, a passenger which needs to be picked up at some point and needs to be brought to some another destination. Well, yeah, this is not very good because we actually cannot evaluate subgoal discovery on this simple model. There are error games, of course, but again, well, the number of subgoals which are natural, well, and are obvious to a human, the number is fixed actually, and usually it's these are doors keys which needs to be well, picked up or opened by an agent in order to reach the primary goal, etc. So this is a fixed system of subgoals. So yes, this could be a rich system of subgoals, but anyway, it's fixed. There's a room task, well-known room task, where the goal is to pass some doorways in order to reach a target room in the environment. And this is actually a very interesting environment in the sense that you can easily modify the room combinations. You can combine and plug in any number of rooms, any combinations, any planning of your environment. But if you look at this task, you see that the agent needs, and it's sufficient for an agent to learn on a single task of looking for doorways in order to be able to solve many instances of these room tasks. Actually, if an agent is able to efficiently look for doorways, then it can arguably solve any kind of room task instance. In this sense, this is, again, not very representative environment. And interestingly, there are few or no industrial benchmarks for Subgoal Discovery, but actually there are many natural examples in the industry, like sales funnel management, where the goal is to guide a customer through a set of steps in order to make an offer. And these steps actually correspond or could be viewed as important sub-goal states. And these are not necessarily linearly ordered sub-goal states. There could be richer hierarchies, but actually we do not see, or we are not aware of, any kind of benchmarks in these directions. Then it was a question for us whether we need to develop some benchmarks for testing all the features that we're going to show. And we came up with the so-called item picking task, which is very simple task, actually, for a human, but not very trivial, or not trivial at all for agents, for HRL, for today's states HRL. Well, the item picking task is quite simple to explain. You have a grid. It's a discrete environment. You have a grid of some dimension, some finite dimension. You have an agent. You have some distribution of items on the grid. And they can be items of different types. For instance, in the example I'm going to speak about, there are only 3 types: green, blue, and red items. There can be some order, for example, partial order on these items. In this particular example, I will use only a linear order of this kind, so green, blue, red, with the primary goal is to pick up the red item, so the maximal element in this order. So there are only 3 actions. The agent can turn left, right, or move forward. And it has some sensors to understand that there is some item in the proximity of an agent. For example, to the right of the agent, left, and so on. Or maybe at the place of the agent, the center. It has also a sensor to understand that it has picked up something, but it cannot detect or memorize the item types it has picked up. It can only sense that it has picked up some item, but no ability to memorize the types of items it has picked up. So actually, this is a very simple task for a human, but well, it is not very well. It is very nice from our point of view generalization of many Subgoal Discovery tasks, because you can plug in any kinds of hierarchies of subgoal hierarchies. So the subgoals in this sense are obviously human. They don't need any separate explanation. And if an agent finds some other subgoal in this environment, then it would be arguably a question whether the another subgoal it has discovered is actually a valid subgoal in this environment. So these items and the order of them is actually more or less strict restriction on the number of subgoals in this environment. And the ability of an agent to identify correctly this subgoal hierarchy is actually a measure, or well, a feature for an agent to explore the environment efficiently and to discover all the subgoals present in the environment. So in the next slides, I'm going to go through the model architecture, which consists of 4 modules: environmental learning, policy learning, Subgoal Discovery model, and Action Planning model. I'm going to start with the first one, the environment model. So in our model, we learn so-called environment rules as expressions of this form, where we have implication between the left part and the right part, where the right part is a some state. It can be a combination of some sensor predicates, like from green. It's an item which tells that a green item is located in front of the agent. And the left part of the implication is a state and an action. A state, again, can be a combination of state predicates. In this particular example, there's only one, right, green, and an action turn right. So this implication is read as follows. So with probability 1, the green item will be in front of an agent if it was right to an agent and the agent has made an action turn right. Okay. Similarly, here we have another rule like this. Like if you have some blue item to the left, we move, then it will be still to the left. Some other item of type blue will still be to the left of the agent, right? And there can be some other rules for this form where we have, for instance, a more complicated state description on the right side of the rule. This rule tells you that whenever some red item is in front of the agent and we move forward, then it will be in the center of an agent, so at the position of the agent, and the agent picks up the red item. Okay, so with probability of 0.2. Is everything okay with my slides? Can everyone see it?
Yeah.
Okay, no problem. So the semantics of these rules, the probabilities which appear here, are calculated on the replay buffer, which is a history of agents' actions, or more specifically, transitions of agent from one state to another state by making some action, right? So actually, the semantics of the probability of each rule is the conditional probability of the post condition or the right part of the rule, conditioned of the precondition, the left part of the rule, right? So it's a common formula. So in this sense, these probabilistic rules, if you call them right like this, is a succinct abstraction or a kind of model of the environment. So the rules which the model, the environment obeys in some sense. But of course, the question is how to learn these rules, because there can be many rules formulated in these rules in this language, and they can have different length, different shape, and etc. There can be rules with different probabilities, and the question is, of course, which rules are more informative in the description of the environment? Which rules should we prefer, and should we select for further usage? Well, if we ask ourselves which rules are most probable in a given environment, for example, with probability 1, then, well, it's a hard question to understand whether there's a rule of this kind with some length k, with probability 1. And this is actually an NP-complete problem to decide for a given replay buffer and the number k, if there is a rule of size, length k with probability 1 on the replay buffer. So this is an NP-complete problem. For this reason, we need some tools to efficiently learn informative rules, in the sense that they have high probability, but at the same time, which have moderate size, small size in some sense. So we come to a min-max problem where we try to maximize probability of learned rules and we minimize their size. For instance, if you have some post, state description post, and we want to understand which rules predict this post most probably and which rules are more or less compact in size, Then, okay, we can consider different rules of different form, starting with the empty premise, like empty premise and making action A gives you post. We can estimate its probability. It can be something like this, depicted here visually. Then if we add some P1, some predicate P1 to the premise of the rule, say the probability grows up. If we add P2, so we have two predicates in the premise, it can be well the case that the probability drops, and etc. So by combining predicates in different combinations, we can actually get different probabilities. And in our model, the algorithm which learned these rules prefers to maximize probability of these rules while minimizing rule size in that sense. So, for instance, if we get a rule with some premise which gives you this probability, and we add any kind of predicate, for instance, P5, which does not increase the probability of the rule, when we do not consider this longer rule, we prefer the shorter rules. It has the same probability as the longer one, and there's no need to add some P5 to the premise of the rule, okay? But of course, there can be local maxima of probability. There can be global maxima of probability. And as I said, finding the global probability maxima while minimizing rule size is a computationally hard problem. For this reason, we use a heuristic in our learning algorithm, which guarantees that up to some rule depth or rule length, you're guaranteed to find global maxima, global probability maxima. But after this rule size, you're not guaranteed to have this. So this initial base rule depth is selected as a hyperparameter of the model. You should specify it related to the environment anyway. But then the algorithm or the learning algorithm works optimistically in the sense that if you add something to the premise of the best rule you found here in this space here, if you have still higher probability for some rule extending another rule in this set, then you take it. But if then at some another step of rule extension, the probability drops, then you cancel a rule extension. You do not consider any longer rules. But of course, this doesn't guarantee that you find the global maxima, because there can be some red maxima, global maxima of this kind here, which you do not find. But at least by modifying this base rule depth and by going optimistically like this, you can find lots of rules which are informative and at the same time have a moderate size. Okay, this is basically the idea of environmental learning. Now I go to policy learning. Policies are expressions of the form here. Well, these are expressions which have some state descriptions at the right side. For instance, here the state description is that an agent is located at the position of red item. It picks it up. And then to the left, if you read the expression, you have a sequence of action states, etc. So this is a combination of action states expressions. For instance, the first policy says that you are very probable to get to the position of the red item and pick it up if it is in front of you. Okay. And this is a loaner expression, a loaner policy here, which is actually a sequence of some transitions. So you are in the position of red item and pick it up. If red item is in front of you and you move forward, and you are in the state where you have red in the front, if red was left to you and you turned left. Okay.
So I have a stupid question just in case I missed a thing. So when we were learning the environment rules, so we were learning this world model, this interpretable world model, did it include the agent itself? Does it include the rules about how the agent itself behaves?
So we have a language for formulation of the rules,
Yep.
which has only the okay, I go to this slide. So in the rule language, you have the signature, the alphabet, which consists only of these predicates. Only of these predicates where, well, the particular indications of sensors, like, for instance, area of red, are instantiations of agent sensor of these predicates with particular constants, like red. Area of red is a ground atom, right, with a predicate area and super constant red. And this language with alpha gives you the language of the rules, so you cannot
but
have
then
anything
the
else.
agent's actions are also part of that language, so we can learn a rule like after the agent does this, the environment changes that way, right?
So, yeah, so yeah, we have a state description on the right, which is a combination of some predicates, or more precisely, a combination of instantiations of sensors, sensor indications. So front of green is an indication of the sensor, of the front sensor, which tells you that there's a green item in front of you, right? And this can be a combination of some sensor predicates, sensor ground atoms, as here, right? And on the left-hand side, you have some action, and you have some state description as well. So the rule tells you that you make a transition by the particular action from one state to another one with a particular probability.
Right, thanks.
Yeah, okay, so the question here is how we use these environment rules for building policies, because you see already that policies are expressions which are, well, which tell you how to get to some state, the right-hand side of the policy expression, from another state by making some actions. So we have here turn left action, we have move here, and actually this is a sequence of transitions that agent can make in order to reach the state center of red and picked up. And each expression has some kind of fitness measure, which I'm not going to explain in detail. I only say that there is some measure which tells you which policies are good, which are bad. But the question is how the policies are learned, how they are obtained from environment rules. So they are obtained in backward fashion. For instance, if you have some important goal, well, it can be a primary goal or a sub-goal, which you have discovered. The sub-goal discovery mechanism is going to follow in the next slides. For instance, if you have these states and you want to understand how you get to the state, then you run environment rule learning with the question, well, what are the rules which lead you to this state? And you get these rules at the end. It can be, for instance, a rule with a single rule, for example, but there can be many. But let us imagine for this particular example that there was only one rule which the environment rule learning has obtained. And this rule looks like from front of red, by making move, you go to this particular state, right? This is an environment rule. And this gives you a first step in creating your policy. Then you ask how you get to this state from the red. How you get to there? You run environment rule learning by asking it how you get to this particular state, what kind of rules you have for getting in there. And there can be different ways of getting there. For example, from this situation where the red was to the left of you and you turn left, or maybe this situation when you turn right, or maybe this situation. There can be many, of course. And you repeat this process by chaining, by consecutively making queries to the environment rule learning algorithm, and you get all possible ways. But the question is, again, how and which policies should be preferred in this particular process of policy search. Again, we prefer to maximize fitness, well, the goodness of policies, whatever it is, and minimize their size. In the sense that if you have a particular well, policy of this kind, which tells you that from front of red, by making move, you go to there, and the loaner sequence, which actually brings you to the goal state from the same initial state, but through a loaner track, not from this one, but through a loaner track, but from the example, the same, exactly the same state from a red, then you throw away these loaner sequences. You do not consider them as plausible. You prefer shorter sequences of this form. Or another situation could be that you get to your important state from another state which is more, which has, well, loaner description. So it's not only from front of red, but it has an additional condition that red was to the right of you. Some other item was of the red item was to the right of you. But if it's the case that the fitness of this loaner policy is smaller or equal to the fitness of the shorter policy, then again, this loaner policy would not be chosen. It would be thrown away. So again, we prefer to maximize fitness, the goodness of the policies, while minimizing their size in this sense. And importantly, we do not run environment relearning from scratch from the beginning. While we do not try to learn everything about a model. We only try to learn the information needed to reach a particular state. Whenever we are interested in some important state, which could be a primary goal or maybe sub-goal discovered by an agent, we run the environment relearning by asking which transitions lead you to a particular state that which you have. We don't because many model-based approaches to HRL had very well, not very nice feature that they were learning all the information about the environment, and that required a lot of space and a lot of time. Here we only rule what is necessary for getting to a particular important state. Okay. Now to the subgoal discovery. Suppose we already have some policies for obtaining some states. Like, for example, you could have some policy, or okay, you could have some policy like here, which tells you that you get to the state when you at the position of a red item and you pick it up whenever you have the red item in front of you and you move forward, and you get to the state when the red is in front of you from the situation when the red is to the right of you. But the goodness or fitness of this policy could be low because as I said, in the environment, there's an order on the item types. Well, there's an order which tells you that you can pick up a red item only if you pick up the green one first, and you can pick up the green item only if you pick up the blue one first. You cannot pick up a red item immediately after you run your agent. It has to go through a sequence of sub-goals, blue, green, red, and the red is the primary goal. But in order to reach it, you need to pass all other sub-goals. You need first to pick up the blue item, right? And you need to pick up a green item, and etc. And whenever you do not have, okay, so I think I slightly missed the order of the items. You have to pick up blue item whenever you want to pick up a red one. Okay, the order is like this. And this means that you cannot immediately pick up a red item if you do not have a blue one. And this policy would be not very efficient in the sense whenever you don't have a blue item. Okay, in some cases the agent can still pick up some red item, but it's unclear how it has managed to do so. We don't have information that we don't have information yet about the order of subgoals and the subgoals present in the model. But we observe that we have some policies and we observe their fitness, we can estimate their fitness, and we observe the history of the agent, the history of agent's transitions. And the idea behind the subgoal discovery is to detect some important intermediate states described by a combination of sensor predicates. The important intermediate states are those states that have the following feature. Whenever we update our policies with these important intermediate states, the fitness of these policies grows up. For example, this particular policy, which could have like fitness like 0.05, if we detect in the history of an agent that there's a state sent of blue and picked up, which means that an agent has reached a blue item and picked it up, if we add the description of the state to the policies we have to this particular policy, in particular, if we update the corresponding environment rules with this particular state description, then we see that the fitness of our policy is 1.0. Each time we have a blue item at our disposal, or whenever we have previously picked up a blue item, we are sure to pick up a red one. And the idea means that we should explore the history of the agent's transitions and identify these states which give you a higher fitness for your policies that you have already learned. Whenever we discover these important intermediate states, we extend the language of our agent. We introduce some invented sensor predicates like has blue, which is a shortcut for this state, center of blue and picked up. This means that an agent has reached the blue item. And then this invented predicate becomes a part of our rule language. In particular, we can learn rules with an extended language, and we can learn policies in this extended language. We can estimate policy fitness, and we can see which policies get more fitness after the language extension. But of course, in general, we may have not a single policy for a state, for reaching a state, but some set of policies, and some of them may be good or not. And this slide explains roughly an idea how we deal with a set of policies, how we estimate an improvement of policy fitness when you have several policies for reaching a primary goal, for example, goal G. Assume we have a goal G, which is to pick up a red item. Okay. Well, we have some policies of this form. We can have several policies actually. We can have two policies like P1 and P2, which bring you to the goal state G. But when we look at the history of agent transitions, we see that only in half of cases when the agent has used these policies P1, P2, it was able to achieve the primary goal G. So there was a case when when the agent followed policy P1, and it has indeed reached the goal G. But there's a case when the agent has followed P1 and it was not the case. And similarly for P2. The idea is that we view this set of policies P1 and P2 as aggregate policy, and we estimate estimate its efficiency or performance after adding these invented predicates. For instance, if we have identified some state description which gives you an update of these policies P1 and P2 as described in the previous slide, and we see that now if an agent follows these updated policies, then it is able to achieve the primary goal G in 100% of cases, for example. Then we are sure to take these combinations of sensor predicates as a subgoal state. And we invent a has-blue name for it and extend the language accordingly, and the agent is able to use this extended language in environmental learning and policy learning. So the idea here is to view a set of policies as an aggregate policies and to estimate its performance before and after the addition or update with the subgoal predicates or descriptions of intermediate subgoal states. Okay. The final part is action planning. When we are able to identify these important intermediate states, we're able to learn policies, we're able to learn environment rules. How do we make action planning? How do we decide what action we take in the next step? Well, actually, when we have policies, the action plan makes actually a policy ranking, depending on the policies applicable in the current situation of the agent and on the previously achieved subgoals. I just briefly explained the idea on this particular example. Okay, so suppose our primary goal state is to pick up the red item, as before. We have some set of policies at our disposal, but some of them are applicable in the current situations, and some are not. For instance, this particular policy could be applicable in the current situation depicted on the left, where we indeed have a red item in front of us. But the question is whether we have already reached a blue item before or not. If an agent knows that it has previously reached a blue item, then everything is okay. We can directly apply this particular policy and make a move forward, and probably we get to the next state. So if we have a policy applicable in current situation of the agent, and all the sub-goals present in this policy are achieved, then we make the primary action in this policy. In this particular case, it is move. It is move action. But suppose the predicate has blue is false in our situation. We have not already picked up a blue item. Then what we do, what action planning makes, it goes to the set of policies corresponding to this particular blue state. Well, pick up a blue item state, right? Again, there could be some set of policies applicable in the current situations, right? We can choose one policy, for instance, in the non-deterministically, but the question is whether all the subgoal predicates in this policy are satisfied or not, whether they are true or not. If all are true, then we can make the primary action of the policy. Again, it is move here in this example. If not, then we again go to the next level according to the subgoal hierarchy, and we ask what policies we have for this particular situation and so on. So actually, this is a ranking procedure which selects the best applicable policies in the current situation and determines whether all subgoals, direct subgoals, are achieved. If not, then the action planning procedure goes to the lower level of execution in accordance with the subgoal hierarchy. Now, to summarize what I've said in the previous slides, the components of our model, the environment rules can be viewed as a succinct description of environment, which is formulated in terms of agent sensors. And policies in our model are just chains of environment rules, which importantly can represent seen and possibly unseen trajectories which lead to subgoals. Importantly, we can estimate the fitness of those trajectories or policies which the agent has never made previously. Because each policy is constructed, is built up of environment rules. For each environment rule, we know the probability, and actually the fitness is computed on the basis of these probabilities. And the important feature of our model is that we can reason, by this we can reason about unseen trajectories. Well, as I said, subgoal discovery is mechanisms which detects important intermediate states, well, combinations of sensor states, which increase aggregated fitness of policies. As soon as we have subgoal predicates, they can be used in the language, in the agent's language. And the action plan is a policy ranking, which I just described in the previous slide. Importantly, what I need to stress is that our model agent doesn't have to make the whole sequence of actions from a single policy, because each time the action planning procedure estimates the position, the state of the agent, it selects the most appropriate policy in the current situation. It estimates whether all subgoals are achieved or not, and depending on this information, the agent selects the next action to make. It is not the case that the agent follows the one single policy from the beginning to the end. Each step, after each action is made, the action planning procedure estimates the next situation and selects an appropriate action. So schematically, this procedure is described as a kind of loop where the model initially, in our model, initially an agent makes n random actions where n big is a parameter of our model, hyperparameter. Well, every n action, the environment rule and policy learning models are activated. Then we have rules and policies. And the action planning is actually the task delegation procedure and policy rank procedure, which delegates the next task to our lower worker according to the subgoal hierarchy. And as I said, well, each time we verify whether there are applicable policies in the current situations. If there are no applicable policies, then we just make a random actions. But if there are applicable policies, right, so then we make a primary action of the policy. Realize whether the primary goal is already achieved or not. If yes, then we finish. If not, then we continue with the whole process. And the subgoal discovery is executed every m number of actions, where m is at least n, and m big is a hyperparameter of a model. As soon as we run the subgoal discovery model, we need to recompute environment rules and policies because the language is now extended and we can learn more information, right? So now some information about experiments in our item picking task. So here I present 3 instances of item picking task environment. IPT0 is the environment where we do not have any subgoals. There's only one red item which we need to learn to pick up. IPT1 is 2 items, 2 item environment, right? And IPT2 is 2 subgoal environments, 2 subgoals. The green and blue items are subgoals here. First of all, we just wanted to know whether the model works at all, because it was not obvious whether these mechanisms, as I described, could learn something better than random walk. And actually, already in IPT0, where the subgoal discovery model actually doesn't work, it doesn't make any work here, or it doesn't bring any information, we see, yes, okay, the model works, it is better than random walk at least. Okay, so when we went to the IPT1, we see that already, it is also important to mention here that the relatively high performance already in IPT0, and where by performance I mean the number of collected red items, the performance was high already after 100 number of learning steps. Only 100 number of learning steps was enough to achieve some good performance here in this particular test. And in other tests, in IPT1 and IPT2, it was sufficient to make 2,000 steps, roughly 2,000 steps to achieve high performance. this experiment in IPT1 has shown that the agent was able to correctly discover the blue subgoal. It hasn't learned any additional subgoals, so no faulty subgoals, for example. And when we were listing the policies the agent learned, actually the algorithm the agent has learned, we saw that they are all actually compact and readable. Well, I'm not sure whether you can read it here in these videos, but actually the text running here is actually the policies the agent has learned and applies right now. And in the last experiment present in this slide, in IPT2, we were interested to know whether the performance of a model with unlimited subgoal discovery capability is significantly better than that of the model where the subgoal hierarchy, the maximal subgoal hierarchy is limited to depth 1, so only one subgoal. And indeed, this limited model with only one subgoal was not better than random walk. It was actually of the same performance as random walk, while the unlimited model was significantly better, of course. So this has shown that actually in this text we learn readable policies, compact ones. We do not have any faulty subgoals, and the performance is actually reasonable. And importantly, the number of learning steps was surprisingly low, which means that the model in these tests is very sample efficient. Now to the pros and cons of our model. Obviously, the model is about discrete domains. It is discrete by its nature, because the language and the rules of the expressions are discrete objects, and it's better suited to discrete domains in general. For continuous domains, the support is limited because, for instance, we need to quantize continuous domains, continuous feature, in order to approach them by our discrete language. And on top of that, at least the current implementation of model is computationally sensitive to the number of sensors the agent has and the number of distinct indications, which means that if you quantize a continuous value with a big number of distinct values, then you get a huge number of sensors and distinct indications. You have a big language, a big alphabet of your rule language, and of course the space of rule learning is big. But on the other hand, you have some very interesting advantages of this model. So the policies appear to be human readable. You can directly plug in explicit constraints onto the agent behavior into the model. So you can plug in particular environment rule or a particular policy into the language of the agent. For instance, with fitness 1, with probability 1, which the agent needs to obey anyway. And this is particularly interesting because it gives you some freedom by posing constraints onto the behavior of the agent. You can verify the learned algorithm, the explicitly given policies. Well, as I said in the beginning of my talk, it can be applied for symmetry detection, for example, to identify some symmetries in your environment, or while detect some concepts which are implicit in your model, like, I don't know, well, turning to the left or turning to the right, like symmetric concepts in some sense. The rule language itself can be extended with quantifiers to account these symmetries, or to formulate complex expression templates. Or in principle, as I remember from the previous talk, we can think as well about going to higher order, although we didn't try it yet, and we're not sure what the complexity will be there, but in general, it's possible. We saw that the model tends to be sample efficient in discrete environments, and actually I'd say nothing about reward function, as you saw. and the model can live with or without reward function, which is interesting because you don't have to construct a reward function for your environment. You just need to give the primary goal to an agent, and then basically that's it. Well, in principle, there are no limitation on the number of subgoals, and shape of the subgoal hierarchy can be any partial order of subgoals in principle, in theory. So we do not have experiments on different shapes of subgoal hierarchy. It's coming. We only have experiments for the linear hierarchies right now. Well, but there are important updates we're going to make in the model in order to improve some interesting features. For instance, as you see, the model is now about the exploitation, about efficient exploitation of environment. But we don't have any methods or tools to efficiently explore. And of course, the combination of explorations and exploitation strategy is very important, which we're going to address next. Well, there is a need to support for complex subgoal scenarios. I will say some words about it in the next slide, in the finishing slide. Like conflicting subgoals, vanishing subgoals, like for instance, an agent may lose some goal it has previously reached, or maybe some goals could be conflicting. You can achieve only one of them, not both of them. Well, this is important to be able to support changing environments or efficiently detect changes in the environment and update your policies and environment rules accordingly. Because it can be the case that agent starts with a kind of atypical part of your environment and learns some information about the environment, but the information is not quite true. It's biased. And then the question is how to update your view of the environment accordingly. Well, at what point should you make this, and etc. Well, and as I said, when you have an explicit representation of the algorithm of the agent, then you can do some meta reasoning on top of that. Well, you can try to identify some important concepts like meta predicates, or you can apply your algorithm to another problem like well, concept transfer, or you can aggregate or compress your view of the environment in order to improve efficiency and etc. So these are our future plans. But we are worried that there are no really good or well-established benchmarks for complex subgoal scenarios, because as we see, we actually need to support different kind of relationship between subgoals, and we need benchmarks to estimate the performance of different HRL models which could work with these relationships, like for instance Boolean constraints in general, like as I said, conflicting subgoals, which is XOR constraint, but actually they could be different Boolean constraints, or vanishing subgoals, right? Or well, there is some situation when a subgoal may be hard to achieve, but once it is achieved, it gives a faster track to the primary goal. And this means that in principle, there could be some measure of difficulty on the subgoals. Some goals may be difficult to achieve, but they give you faster trajectories to the primary goal. It could be, well, you might think that these requirements are kind of mathematical abstractions, but they are not, because there are many cases also coming from industry which tell you that they naturally appear in real world domains. Like for instance, well, Boolean constraints, like at most one subgoal which can be achieved at the moment. Well, there's a well-known case in medical examination that you cannot do or have, or well, 2 X-rays at one time, or one right after another, etc. Or it's quite common that, for example, blood test is valid for a time period, like this. Well, this subgoal, if you use it as a subgoal, well, of making it blood test, it vanishes after some time, and this means that in some kind of medical examination tests when you need to learn optimal examination strategy from patient records. If you do this by RL, you need to account to these relationships between subgoals. And similarly, different other scenarios like sales funnel management, like in order to avoid aggressive ads or while accounting for periods of customer inactivity, etc. It looks like we really need to account for these situations, and we need to look at some industrial data and benchmarks which could arise from real-world application scenarios. And I would actually be very interested to discuss this particular topic of benchmarks, what kind of benchmarks you view important in this field, and which application domains could be most informative for this or that subgoal scenario discovery test. All right, so I thank you for your attention. I hope I was almost in time, and I would be very pleased to answer your questions.
Thank you very much for that presentation. I like to joke that in works on interpretable ML, the quality of the work can be measured by whether you have the actual policies on your slides. You had them in small print, but you did. So that's really cool. And speaking of the benchmarks, I have a vested interest in promoting some healthcare benchmarks because I'm working in my day job on some interpretable reinforcement learning for healthcare, which is definitely a domain where safety concerns drive us towards interpretability, right? And you can search for towards effective patient simulators, which is a paper we've recently published, where we try to come up with as much as possible, as good as possible benchmarks that are healthcare related. This is still a field that's, as you've correctly noticed, just developing. But there is a lot of work on that. Yes, speaking of benchmarks, did you try to? So you actually asked Paul if they tried to compare black box method to interpretable methods. Did you do that?
Not yet. So actually, I think when comparing our model to other models, we should first compare to interpretable ones, because it's very interesting to measure not only the performance in terms of like picking up the items in our test, but also by measuring the readability, for example, conciseness of policies as another measure, or some kind of other measures which could be formulated by people working in real-world domains, because this is yet another dimension of comparison between models. And since we claim that our model is interpretable, of course, yes, the question of explainability and readability for large learned policies, for large sets of policies, is a separate question, right? But at least as soon as the model is inherently interpretable, which means that there is explicit language for formulating the learned algorithm. Well, I want to mention that this is would be an interesting dimension for comparison a model with another ones. But if we speak about performance of models, we see that most black box models, which are based on deep learning approaches, for example, require indeed lots of steps, lots of learning steps. And here, in this particular test, we have from 100 to several thousand steps in order to achieve reasonable performance. It would be interesting to see how many steps the black box model would require in our item picking test, for example. That would be very interesting to see and to compare sample efficiency of the models.
Yeah, great. So we have some further research identified. Yeah, so you say this model has pretty high sample efficiency, right? But on the other hand, I guess it would be pretty computationally complex for every step, right? Compared to a backprop on a simple neural network, which one's more complex? Which one takes more compute, and why?
Well, at the moment we do not rely on any solvers or tools that could solve optimization tasks, because yes, I mentioned in my slides, but we have several minimax optimization tasks, like optimization of environment rule learning, where we need to maximize probability and to minimize rule size. Yeah, we could actually apply some solvers to do these tests, right? This could be an interesting point as well, but at the moment we are concentrated on heuristic-based algorithms, which could be tuned by changing the base enumeration depth, which gives you the complexity of rules. And the complexity of rules in the current implementation can be tuned up to the environment. And as a next important step, it would be interesting to understand whether we can live without these hyperparameters at all. Whether we can learn these base rule and enumeration depth, for example, automatically, in order not to determine it manually and not to initially tune the model to, in this sense. From the point of complexity, I think we still need to make comparison in a sense with black box models, with deep learning-based models, in order to understand the exact computational complexity and performance in terms of memory consumption, etc. But I think I didn't have numbers about the cost of computations for particular experiments, but maybe my colleague Alexander have these numbers. But these are not like extraordinary numbers, I would say. So I need to consult my colleague Alexander to give you exact numbers on that.
All right, Alexander, do you want to jump in or?
So I don't know whether Alexander can provide these numbers right now.
Yeah, sure. It's not. It's not essential. I'm just being curious. Yeah, well, but as far as I understand, you have, since there is this hyperparameter, right? You have a way to artificially tune up and down the computational complexity of the method, which could prove it really useful, right? Depending on what kind of resources you need. A particular comparison with the deep learning methods would be interesting, of course. But yeah, it's nice that there is this. Like flexibility built in.
Yeah, in particular, you can try to prove the optimality of learned policies by considering these, for instance, the base enumeration depth in the limit. For instance, if we imagine that the base enumeration depth is unlimited, then it would be possible to study the optimality of the policies. It would be possible to tell whether the learned policies in this case could be optimal or not. And it would be interesting also to understand how far we are from optimality when we set this or that base enumeration depth, for example, right? Regarding the cost of computation, I think that each round here in these experiments, each instance of this experiment took several minutes. like several means, and in each experiment we made several runs, and we averaged the number of picked up items on these runs, and this is how we got these numbers here. Well, this means that, for example, in these instances of IPT, where 2,000 steps were sufficient, like we computed the whole one instance like several means, like 2,000 steps is like several means, like 2 or several means or so.
That's pretty impressive. Okay, yeah, so does anyone else want to ask questions? I'm hogging the microphone here.
Yeah, I'm going to ask one question. Yeah, so thanks for the presentation. It was very interesting. And actually, going back to the question of benchmarks, I think that we are solving a very similar problems. And so all the benchmark we use and I used in our work could be applied here as well. And so that would be interesting to compare as well the performances. Yeah. So I have a question. In fact, so first, it seems that what you are trying to optimize, as you don't have a reward function, is basically the probability of reaching a goal. So
Right.
the whole method is formulated like this. And so if you now introduce reward functions, so what will you need to modify, and what will be the impact on your method?
When I said that our model can live with reward function, I mean that you can simulate the reward function by our probabilities, by our fitness measures, etc. So you can modify in the way that which accounts for the reward function we have. Okay, but in general, you do not have to have a reward function. This is correct.
Okay, but so can you really simulate completely the, for example, because you need to compute, for example, the value function in a state, and so that can be done completely by translating everything in terms of probability.
Yes, so yes, you can modify the formulas for estimation of probabilities for your rules or for your policies in a way which accounts for the reward function.
Okay. And currently, I mean the very important hyperparameter in the current method is this hyperparameter n, in fact. So you need to because this is where the exploration happens. So you need to generate a data set that's diverse enough for your method to start learning. And so I guess it can happen that you learn some policies that are applicable, and then you are stuck with this policy, and you can never improve on that anymore.
Exactly. So this is related to the question I mentioned by updating your policy sets while the environment changes. So this is actually the similar problem. So you learn some policy. It could be the case that you learn it in some atypical part of the environment, or if you make some small, not sufficiently big number of random actions initially. This could be again the case that you learn some faulty policy and need to decide how and when to update this faulty policy. This is correct.
Okay. Yeah, so so your method has a nice property that you can control the size of the formula you want to learn.
Yes, but nice property, yes, so we can control. We take control on the size, on the informativeness of the policies and rules, which is really important because, well, this is an well, This is a common problem in AI in general, that you need to learn something which is informative and which is compact, more or less. Mm-hmm. So in our particular model, this is concerned with rule learning, where we want to learn compact rules, but which describe our model very informatively, or more or less informatively. Yes, it is important to mention, and I'm sure you see that in our model, the rule language is propositional. It's not first order, actually, as I just described it. Yes, you can introduce quantifiers. You can apply the same procedure, and you can extend the model to support quantification. But in the current implementation, it's propositional because you have description of states which are ground items, right? And it would be indeed interesting to compare the performance of your approach with this propositional approach in order to understand on this particular item picking test, for example, whether first order features are really interesting and give something better than performance we achieve here.
Because I understood that part, then, because you had predicates that you apply, you apply those predicates on some objects, but at the end you use just a propositional logic to represent everything.
Yes, exactly. So the rules are actually propositional because each time you have ground items, the description of state is a combination of ground items where you have some predicates applied to some object, right? And you have combinations as state description. So this is important to note here that these are actually propositional statements, but they can be extended with quantification.
Okay.
Like, for instance, in the robotic example, where you have many similar models, you can say that for any module, something holds, for example. And this would be a statement about the symmetry.
Yeah, so if you move to first order logic, you could learn even more compact policies.
So in this particular robotic example, again, this could be a different talk, actually. I don't have time right now to speak about it in detail, but in that particular work, the quantifiers were very important. The rules were indeed first order, and it was really important in order to solve this exponential implosion problem. Because only when you're able to identify functional symmetries in these robot locomotion tests, then you are able to learn efficiently. Otherwise, it's infeasible.
Okay, thank you.
I have a rather naive question. Is it possible to apply this to, say, mathematical proof theory, like automated proving? Is there a link between this research and that, or is it totally unrelated?
Well, actually, this is interesting. We didn't think about that, but if you can formulate your problem as an environment, as a RL problem, why not?
Yeah, I can imagine that you could train on existing proofs, for instance, or simple proofs, and then build your way up to the more complex ones. Okay, well, yes. Just a thought.
Yeah, thanks indeed. Yeah.
And another thing that I was wondering about, but which is also stretching the context a bit, is what would happen if you applied fuzzy logic, as Paul mentioned a bit about fuzzy logic. Is that, what would that mean to? Would it be viable to implement that somewhere, or is it stretching it a bit?
I'm sorry, maybe I didn't quite understand your question. So you're asking whether we compared to fuzzy-based approaches. Am I correct?
Yeah.
So we are aware of papers where indeed fuzzy rules were applied, but the model was quite different for us. For instance, there's a work where the authors used genetic algorithms to learn fuzzy rules, but this means that you learn the whole population of rules at once. You evaluate this population on your environment. You estimate the performance of this set of rules, and then you update this population somehow. Here, our model is conceptually different from that work in the sense that we do not learn the whole bunch of rules at once. The environment rules are learned only on demand when we are interested in reaching a particular goal state, when we execute the environment learning algorithm when needed. And the important feature is that we can, by this, we can reason about unseen trajectories of an agent, which is also possible in this population-based approach. But we are more targeted here. We are more targeted. We do not learn all policies, for example, or all rules, as I said, which is not very nice for complex environments. We are more targeted in learning.
Mm-hmm. Okay, well, thank you.